Okay, so we're continuing with related rates, and we're still working on that one with the cone on there and the volume of the cone and what really is happening. So if we look at this, let's just review really quickly. We have a cone here, and we're filling it up with water. And as we're filling it up with water, the things are happening here. And so we want to know, here we have this one here to be a radius of 4, and this is of 10. And when we continue looking at this radius here and this height is always going to be proportional to that. So as it keeps getting filled in or decreasing in water, you're still going to have the same proportion. It forms a right triangle right here. If you see this right triangle right there, that you could see this here is this height, the same height as over here. So this height is the same as this height, and this radius is the same as that radius. So it forms a right triangle all the way there. And so therefore, this triangle and the big triangle are going to be proportional. So this R is to 4 as H is to 10. And so we use that information to be able to solve these problems that we're working on here. So this is the problem that we have here. And so our radius here is 3, and the height of it is going to change on there. But it's also 10. It's going to go up as high as 10. And we are talking about a cone, and the volume of a cone is 1/3 pi r squared over h, which I told you, when it's written this way, it looks like there's a lot of variables, but there really isn't on there. The pi is actually a number, a constant. So it would be, I would continue putting that together so that you see that it's only the radius squared and it's the h. And then this pi over 3 is just a coefficient. So we treat it as a coefficient when you're taking the derivative or manipulating it in any way. And then that's what the volume is going to be on there. So looking at it, that might be a better way to look at it. And so we know that the radius and the height are going to be proportional, and they're going to be a ratio of 3 to 10. One fraction equal to another fraction. We could do the cross multiplication, and we get, depending on what we want, we could have r in terms of h or h in terms of r. And then we could actually find the volume formula here. So we take this volume formula, and we could actually replace, if I wanted a function in terms of r, that means only r's, I have to get rid of the h. So I replace the h, and I get this formula so that it's only r. So I replace the h here with 10 over 3r, and I do the same thing to this one here to get them all in terms. I get rid of the r and replace that with 3/10 h, and then that gets that volume formula there. So notice how it's still the volume of this cone, and this is still the volume of cone, but this one only has it in terms of r, this one has it in terms of h. And then I could take the derivative. It's much easier if I take the derivative when there's only two variables. So I only have v and I have r. If I take the derivative here, this does give me dv dt, and we're taking the derivative in respect to time. And that makes sense because the time of the cone is getting filled in water over time. So everything we're taking in derivative as time is passing. How is the radius changing? As time is passing, how is the volume changing? As time is passing, how is the height changing? So what this is saying is that the volume is changing with respect to time as this number r squared, as the radius is changing with respect to time. And then here's the same thing. The volume is changing with respect to time as time is passing, the same way as the height is changing with respect to time. And then that's the height on there. So we're going to use these two derivatives to answer these questions down here. So problem number 5, when there is 6 inches of water in the cone, well, that we're going to have to translate the words into math language. So when there are 6 inches of water in the cone, that's telling me right there that we have some information, and they're giving us that the height is equal to 6 inches. And then the height of the water is increasing at 7 inches per minute. So that is telling me, increasing tells me that it is a rate of change. So, and it's the rate of change of the height. So they're telling me that dH dt, in terms of, because the units are inches per minute, is going to be 7 inches per minute. And then how fast is the volume of the water in the cone increasing? So we want to know, again, it's how fast, that's a rate. So we want to know dV dt. We don't know what that is. So I'm having information on h, and so they're giving us the derivative of h, which is how the rate at which the height is changing with respect to time, and we want to know dv dt. So which one of these formulas am I going to use? This one here or this one here? And it's easy to see because this one has all the h information that I would use this formula right there. So then you would do dv dt is equal to, you know what, I'm just going to do it in the green so we could see that. dv dt is going to equal 9 pi over 100, and then the h squared is going to be 6 inches squared, and then the dh dt, we're going to treat this as a variable and replace it with the 7 inches per minute on there. Now notice how we have inches squared, and then I have times inches. So I'm going to get inches cubed, which makes sense because we're talking about volume, and therefore the units have to be cubed because it's a volume formula. So I use my math. I multiply this out. Remember, if this is a fraction, I'm going to make this a fraction as well, and that's already a fraction. So it's going to be numerator times numerator times numerator, and then divided by the 100, which is going to be 1 minute down there. And so when we get that and we put that into our calculator, we get that dVdt is approximately 71.25 inches cubed per minute. And that gives us the answer. You are going to have to write a sentence on there describing on there the water is increasing at a rate of approximately the rate of 71.25 inches cubed per minute. And so that's how you do problem number 5. Now let's say that we are doing problem number 8. It's still talking about this one here. And so we're given that dV dt is 5 inches cubed per minute. Well, this tells us that we are talking about volume. Even if they didn't tell us volume, we know that the cube is going to be talking about volume. So we're given information here that dV dt is equal to 5 inches cubed per minute. How fast is the surface radius of the water in the cone increasing when the water height is h is 4. So we know h is going to be 4 inches. It's not saying that the height is changing. They're saying add exactly when h is 4. So therefore it's just 8. H is equal to 4 inches. But we want to know when the surface radius is going to be, how fast is the surface radius changing on there. So the surface radius is this one right here, the surface radius on there. So we want to know what dr dt is. So that's the information that's given to us. So which one are we going to use? Well, here it's a mixture of both. They're giving us h, they're giving us dr dt. So now you have to look at which one do I use, because this one has no r's, this one does have r's but no h's. So how are we going to do that? Well, if we're given h's and I want to do r's because we're giving us the dr dt, I want to use this formula. But I also know the relationship between h and r. So if they're telling us that the height is 4, I am just going to replace this with 4 and find out what r is and then be able to replace it. So I know that I am going to be able to find out what r is because I am going to take r, which ends up being, what is r? Hold on. Okay, it's not coming down. 3/10 h. Okay, so it's going to be 3/10, and then h is 4, so it's 4 over 1. So r is going to be 12 over 10 on there. And so that's going to reduce to 6 over 5. So now I know r, and I want to find out what dr dt. I'm given dv dt. So I am going to use the formula dv, and I think I used this is purple. Okay, so I am going to use that. So I am going to get, I am going to have dv dt is equal to 10 pi over 3. And I know what r is. And so I'm just going to write down dr dt, that's the formula we're using. So dv dt, I'm filling it in. So it's inches cubed over minutes. And then we get 10 pi over 3. R is 6/5, and it's inches because that is also inches. So we have inches squared, and then dr dt on there. So I need to solve it. I'm treating it as a variable. I need to solve for the rate as the radius is changing as time is passing on there. And so what we want to do is we want to move all of this over. So I am going to divide by inches squared. So the inches cubed is going to cancel. And then I'm going to divide all that information over on there. So when I do all that, it is approximately 0.33 inches per minute is approximately what we get for the DRTT. So you want to write your sentence again, how fast the surface radius is changing at a rate of approximately 0.33 inches per minute. And so you write your sentence, and that's what you have it. Let's do one more, number 9 on here. Number 9, they're giving us again the volume at the rate that the volume is changing, which is the same as number 8. So that's good. How fast is the exposed water surface, a circle, increasing when the water height is 4 inches? So they're giving us this formula here, S equals to pi r squared. So we want to be able to, how fast is the water surface? So that's this, the S, the water surface, compared to the radius on there. So we want the actual rate of S. So that means that this is just S. So I'm going to have to take the derivative on that. So in order for me to take the derivative on this, it's going to be ds, and I'm going to take it as it's changing with time. So dsct, pi is a number. So therefore, I'm going to leave it alone, the coefficient there. And so it's going to be squared. So it's going to be 2 pi r 1, and then I have to take the derivative of the inside. The 2 is where this 2 came from, and then I have this to be 1 right there. And then I take the derivative of r, and we get dr dt. So the information that we have here, we have the derivative of that. We're given that dv dt is equal to 5 inches cubed per minute. We are also given that the height is going to be 4, which, if you notice, that was what problem number 8 was. The height was 4. The dv dt is the same as well. So we have two of the same things here. And so we already solved what dr dt is. So we already know this part right here. And we already know what r is because we solved r up here as well. And so now I just have to fill it in and solve for it. So I already know most of this. I know that ds dt is going to be 2 pi. I already know that my r is 6/5 inches. And the dr dt is going to be, and I would store this in the calculator so you could get a better answer and not cut it off and get a truncated answer. So we want the exact answer on there. And so I know that dr/dt is a rate. So it's inches per time, which is minutes. So I'm filling this as a variable. R, we already know the 2 pi, and we're solving for this. And then notice how we have inches and inches. So you're going to get inches squared because the surface area, the water surface is the area on there. So that's where you're going to get the inches squared for area. So we get ds dt, when you calculate it, is going to be approximately 2.5 inches squared per minute. So in this case, it's positive, so we know it's going to be increasing. If it were negative, it would be decreasing. So we could say the exposed water surface is increasing at a rate of 5 inches squared per minute. Make sure you write a sentence on there. And so that would be that on those. You could do the other problems on your own. Okay, very good.